Hello Year 12 further mathematicians. Just going to do the second half of subsection 2.3 modulus argument form. And we're going to go into a little bit more detail on some of the shortcuts you can use to multiply and divide complex numbers when you're in modulus argument form, and go into a bit more detail as well what actually is going on geometrically when you are multiplying and dividing numbers in modulus argument form. So let's consider two complex numbers, z1, z2. If we wrote them in modulus argument form, they'd be something like this. So you'd get r1 cos theta 1 plus I sine theta 1, where the r1 represents the modulus and theta 1 represents the argument. And z2 can be r2 cos theta 2 plus I sine theta 2. Now let's suppose we multiplied these two complex numbers. So you took them both and you multiplied. Now there's a relatively long algebraic process where you use expanding brackets, trig identities, collecting like terms, etc. And all of this simplifies to r1 times r2 cos theta 1 plus theta 2 plus I sine theta 1 plus theta 2, if you bother doing the algebra. Now what we've been left with is again a complex number in modulus argument form. The modulus is a bit at the front and the argument is the angle. So what is actually happening when you take the product of two complex numbers, you can work out the the modulus, if you just times them together. So you can work out the modulus without even doing the long process of multiplying them. And similarly, the argument of the product of two complex numbers is just the addition of their angles, or the addition of their arguments, arg z1 plus arg z2. Now what this means visually is if I drew two complex numbers, just say this one is z1 and let's just say this one is z2. So z1 has an argument theta 1, z2 has an argument theta 2, and we've got r1 is the length and r2 is the length there. When you multiply these complex numbers, the answer has a modulus of the product of these two. So whatever these lengths are, you would times them. So it's like an enlargement. So in other words, an enlargement. And the angle would be the addition of these two. So you add them together, which is, in other words, a rotation. This is one of the useful properties, geometrical properties about complex numbers, is because it's really easy then to express enlargements and rotations using complex numbers, whereas those things are really difficult when just using real numbers. So the answer would be something like this. So that's z1, z2, where the length is the product of both moduluses, and the angle is theta 1 plus theta 2. Okay, so that's what's happening geometrically when you multiply complex numbers. What happens when you divide them? Well, if you bother to do r1 cos theta 1 plus I sine theta 1 over r2 cos theta 2 plus I sine theta 2. If you used times in by the complex conjugate, using trig identities, expanding brackets, collecting like terms, all of that stuff, it would simplify to r1 over r2 brackets cos theta 1 subtract theta 2 plus I sine theta 1 subtract theta 2. Like so. That would be the shortcut. You divide the moduluses and you subtract the arguments. So in other words, without even working anything out now, you can use the pattern of z1 over z2. If you wanted to work at the modulus of that answer, it would just be the individual moduluses divided by each other. And if you needed to work out the argument of that answer, you wouldn't have to do any algebra at all. It'd just be arg z1 subtract arg z2. And if you want to interpret this geometrically, then z1 over z2, the modulus is the opposite of an enlargement, or you can enlarge by a fractional scale factor, and arg z1 take away arg z2 would be rotating by the opposite direction. So if you want to label that on visually, so you would take z1 and you divide it by this length, so it'd get a little bit shorter, but also the angle itself would rotate theta 2 back in the opposite direction. So that angle there is theta 1 take away theta 2, and that's z1 over z2, and that length is r1 over r2. So that performs the rotation in the opposite direction and makes things shorter. It's like a dilation rather than enlargement. Let's have a look at some common mistakes which we need to consider. So this top thing is modulus argument form. So if you end up as being requested to write anything in modulus argument form, it has to look like this. And the shortcuts I've just discussed on the previous page only work when things are written in modulus argument form. If they're not, then those shortcuts become invalid. This number looks almost like it's in modulus argument form, but it's not quite there. There's a negative sign which makes this not modulus argument form. And most people fail to spot this in exam questions, and they think this is modulus argument form and they get a question wrong. If you get a number which looks like this, where there's not a plus sign in between, there is a trick, and the trick is you rewrite this as r cos minus theta plus I sine minus theta. The minus sign gets inputted in the argument. Okay. One of the reasons why this works is because cos minus theta is actually the same as plus cos theta, and sine of minus theta is equal to minus sine theta. And if we work backwards from both of those, we would get the same answer. So that's one reason why. Another geometric reason why is if I just labelled this as our complex number, call that W, which was r cos theta, actually call that Z, r cos theta plus I sine theta. So that angle is theta, this length is r. Now, if you look at what has actually happened when I change to W, I've just changed the imaginary part to a minus. That is the complex conjugate, actually. And if we drew that in, the real number is exactly the same, and the imaginary number is just switch sign. So there'd just be a reflection in this direction. And that's W, which is R cos theta minus I sine theta. Okay. Now, if you want to work out the modulus of this, by what's happened, which is just a reflection, then obviously the modulus stays exactly the same. A reflection doesn't change the size of that line. And also because it's a reflection, the angle is the same. However, when you're asked to work out the argument, it's the angle made with the positive real axis, and if you go clockwise, it's negative, minus theta. And that's why that's minus theta in both of those from a geometric point of view. R is exactly the same, because that's a positive length, doesn't change. The angle is theta below the axis now. That's why you change the sign to a minus theta, because it's going clockwise instead of anti-clockwise. Hopefully that makes sense. But this trick is going to be needed in many of the examples in the exercise you're about to do. Okay, let's try this easy number one. I'm going to express the following in the form x plus iy. So we've been given a question in terms of modulus and argument, but we're going to end up in the normal form. But we're going to use the tricks of modulus and argument. Okay, so I want to do a product. Okay, the first trick is modulus of z1 times z2 would be the moduluses times by each other. So that would be 2 times 3, which is 6. The argument of z1 times z2 would be the addition of z1, arg z1 plus arg z2. Now the problem is, if you kept going with this, you're going to get this wrong, because paying very close attention to z1 and z2, this one is in modulus argument form, but this one is not. So I can't use this shortcut until I've rewritten this in modulus argument form using the trick from above. So this is the same as 3 cos minus 2 pi over 5 plus I sine minus 2 pi over 5. That now is modulus argument form. So that's equal to arg z1 is pi by 15 plus arg z2 is plus minus 2 pi by 5. Work this out on a calculator. Pi by 15 plus minus 2 pi by 5, and you get minus pi by 3, or minus a third pi. So now you know the modulus of the answer. Now you know the argument of the answer. So in other words, z1 times z2 would be this modulus, cos theta, which is minus pi by 3, so this argument, and that would be the answer in modulus argument form. If you want the answer in x plus iy, so the normal form, you just have to expand the brackets. And you should technically know what cos of minus pi by 3 is. So times by minus pi by 3, you get 3 times by the sine version as well, you get minus 3 root 3 I, and that would be your final answer for that one. Let's do something similar with part B, z1 over z2. Probably the first thing you should check is, are these numbers in modulus argument form? And they are. You've got pluses, same arguments, pluses. Happy with both of those. So now I can use the shortcuts. So z1 over z2, I need to work at the modulus, which would be modulus of z1 over modulus of z2, which is root 2 divided by 2. That's a third. Right, arg z1 over z2 is the subtraction or the difference between them. Pi by 12, subtract 5 pi by 6. What would that be? Don't want to work anything out. I can use the calculator. -3/4 pi. And therefore your answer would be z1 over z2 would have this modulus, cos this argument plus I sine this argument, and that would be it. And if you want this in the other form, x plus I, just expand the brackets. Again, you probably should know what that is anyway, but no one likes to show off, so we will just use the calculator. Okay, so that's -1/2. If we change that to a sine, -1/2 as well. I. And that would be it. Now the questions I would like you to do start on page 27, exercise 2D. And there are lots of them, or lots of different parts anyway. So let's do question... Okay, let's do question 2. Question 3, and we'll do the parts B, D, G, and H. Question 4, we'll do B and D. I'll try question 5 as well. That'll be it.